Hi, so this is Maharshi Ray, and I'm from the Center for Quantum Technologies. I'm a final year PhD student. I'm going to talk about the strategies for quantum races, and this is a joint work with Troy Lee and Miklo Santa. So imagine that Alice and Bob have identical quantum computers with them, and they have a database with exactly one marked item. And the goal is to find this marked item before the other person, and the winner gets $1. So the question we're asking is, what kind of algorithm should they be running? So the main motivation for this work was to understand how Bitcoin mining would be influenced by quantum computing. Uh, Bitcoin mining, in an abstract sense, is a race to solve a computational search problem. So therefore, quantum miners could be using Grover's algorithm to find this marked item quicker than any classical computer. But the question is, how exactly would they be using this Grover's algorithm? And secondly, whether these strategies can destabilize the Bitcoin protocol. So here is a one slide summary of Bitcoin mining that is relevant to us. So Bitcoin is a decentralized currency where the transactions are packaged into blocks and stored in a public ledger called the blockchain. People who create these new blocks are called miners, and the right to create a new block is given to that miner who wins a particular contest to solve a computational problem, which is called the proof of work. So it works as follows. So suppose capital H is the header of the block that the miner is trying to add to the blockchain. Then he or she adds, concatenates this value X, also known as nonce, to this header H, and then takes a hash value. This H is a prefixed hash function, and then sees if this value is smaller than some parameter t. This t is fixed so as to fix the hardness of this network. So for example, currently one needs to do about 10 to the power of 16 hashes to mine one Bitcoin. So the background picture that should be kept in mind is that one has to search for a marked item in a very large database. Forking is another important concept in Bitcoin mining, where like if two miners solve the search problem at almost the same time, then it is bad for the security of the protocol. And also, of course, it wastes resources. So the key differences between classical and quantum mining are as follows. So in a classical search algorithm, you can just search for an index, and if you find the marked item there, you stop, or else you can just continue. And if you are using Grover search, however, you have to select a time beforehand, and then when you make that measurement at a particular time and you find it, then you stop. However, if you fail, then you have to start the algorithm from scratch. So it seems like it's kind of a disadvantage in the quantum case, but we know that the success probability in the classical search increases linearly with time, whereas in Grover, it increases quadratically. In the worst case scenario, the classical search takes time n, whereas Grover search takes time pi over 4 times square root n, where n is the size of the database. So coming back to our problem, suppose Alice runs naively the Grover's algorithm for the worst case scenario, that is pi over 4 times square root n steps. Bob can do something more clever. He can run the Grover's algorithm for like 10 less steps. By doing so, Bob has a slightly lower success probability, but he always answers first. So therefore, with a high probability, he wins the $1. So here's a dilemma, like whether the player should wait and increase their success probability or go early and answer first. So to analyze this situation, we look at this class of games called quantum races. We model it as following. The players can decide to measure at these discrete times, 1, 2, 3 up to k. So in the earlier example, k was pi over 4 times square root n. And the success probability is described by the function pt, which is a monotonically increasing function. A strategy in the game would be a probability distribution over these times. So a quick recap of Nash equilibria. The intuition behind the Nash equilibria is that none of the players should have the incentive to deviate from their strategies. So, for example, if Alice and Bob's payoff matrices are denoted by A and B, the expected payoff for Alice when she plays X and Bob plays Y is X transpose AY. So if X comma Y is a Nash equilibria, no incentive for Alice to deviate means that if Bob plays Y, then no matter what Alice chooses to play, her expected payoff cannot be more than X transpose AY. And similarly for Bob, whenever Alice plays X, then no matter what Bob does, his payoff will never be more than the expected payoff of X transpose BY. There is an approximate version of this as well, and here the players are allowed to deviate only a slightly by a slightly a small amount of epsilon, and this is also very useful in most practical applications. So we study both two players as well as multiplayer quantum races, but we talk about the two player now in more details because it's easier. So let A of S comma T denote the payoff when payoff of Alice when she measures after S steps and Bob measures after T steps. So A of S comma T is given as follows. So suppose Alice measures before Bob. In such a case, Alice just needs to win. So the probability is PS. But suppose Alice measures after Bob. In this case, Alice not only needs to win, but also requires that Bob has to lose, which happens with probability 1 minus PT. Now, in case this second condition is true, that is when Alice and Bob play at the same time, then two things can happen. One, Alice has to win and Bob has to lose, or in case both of them wins, then the $1 is shared between them. And Bob's payoff matrix is just a transpose of Alice's payoff matrix. So in order to analyze, we study this variant of our game called the Stingy Quantum Race. The only difference here is that in case of ties, nobody actually wins. So for example, in this case, this term, the second term is 0 in our stingy quantum races. Why do we study that? The simple answer is that it makes the payoff matrix nicer in some sense, and it allows us to solve equations of this form ay equal to 1 easily, and we get an explicit form of the Nash equilibria. Also, this game has a very nice support structure. For example, if x and y is a Nash equilibria of this game, then the support of x union support of y forms an interval which contains the last time step, which is k. So we completely characterize all the Nash equilibria for this stingy quantum race. And they are of 3 types: coinciding, alternating, coinciding. For this talk, we'll just focus on the coinciding equilibria, where the support of x and support of y are the same. So for example, here is an illustration. So there is this result we have that our game, the stingy quantum race, has a unique coinciding, always has a unique coinciding equilibria. And for this case, when the size of the database is 10,000, and we have like 2 players, the small n denotes the number of players, then the strategy, the Nash equilibrium strategy is given as shown here. So here the equilibria, the support begins at about 35 and k is about 78 here. Okay, so in order to give a more a better understanding of this starting point of these equilibria, we introduce this parameter called the density, and intuitively it tells us how smooth the P function is. So we say that a race is like L dense if the difference between Pi plus 1 and Pi is at most L over K for all I. So for example, in the Grover's case, we have L is equal to pi over 2. Just keep in mind that for Bitcoin application, this L is like pi over 2, whereas the K is very large, like as we discussed earlier. It's about like, it's very large, of the order of 10 to the power of 11. So the ratio L over K is like very small. So here are the results we could show in the 2-player case. So we showed that the support of the unique Nash equilibria is an interval where T star is such that PT star is about square root 2 minus 1 plus a very small term. The probability of a tie when 2 players are playing this unique coinciding equilibria is very low. And third, this unique coinciding equilibria in the stingy quantum race is actually a very good approximate Nash equilibria for the corresponding quantum race. The main idea is that these 2 games, the actual quantum race and the stingy quantum race, only differ in the cases of ties. And then we use the idea that the chances of collision is very low. So using these 2, we can prove this theorem. And next, we also show that the payoff of this approximate equilibrium is very close to optimal among all possible symmetric Nash equilibria of this game. So let's look at this a little bit more clearly. So due to this result by Mangasarian and Stone, one can compute the Nash equilibria of a game given by matrices A and B using this bilinear program here, which is a program in variables P and Q, which are probability vectors, and scalar variables alpha and beta. They show that a Nash equilibria X and Y gives a feasible solution to this program with objective value 0. And also the other direction, that any feasible solution of this program with the value 0 is a Nash equilibria of the game given by A and B matrices. So in our case, like we are using a symmetric game, so B is equal to A transpose. And furthermore, since we are restricting ourselves to like symmetric strategies Q and Q, the above program just simplifies to this form here. And then we use observation in our game that for the race given by P1 to Pk, the summation of the A plus B, in this case, like A plus A transpose, turns out to be a very nice form, which is equal to like P times the all one vector transpose plus 1P transpose minus PPT. So plugging this above plugging this back here, we get that we get this following program. And now we see that this is essentially a convex quadratic program, and we can solve it in polynomial time to high accuracy. And also we know some results that there's a dual minimization program with a matching value. So our strategy here to prove the theorem is to exhibit feasible solutions to this dual minimization problem. And that way we can bound the value of alpha. Okay, so finally, we also talk about the multiplayer case. So the main idea here is that we try to relate the payoff matrix of Alice in an n-player Stingy quantum race to the payoff of Alice in a two-player asymmetric Stingy quantum race against a more powerful opponent. This allows us to port many of our results from the two-player version to the multiplayer version. For example, here we show that in an n-party Stingy quantum race, there's a unique coinciding equilibria. And the starting point is T star, where PT star is now like theta of 1 over n. Similarly, the unique coinciding equilibria in the Stingy version is a very good additive approximate equilibria in the corresponding quantum race. We also show that the probability of a tie using this unique coinciding Nash equilibria is at most 8 E and L over K, where E is the Euler's constant. So lastly, like if we plug in the Bitcoin parameters, so L is like pi over 2, K is 10 to the power of 11, N, which is the number of players, it's a bit of unknown, one would say, but probably it's believed to be in thousands or at most a million. But regardless, that still makes this probability of collision to be still very low. So we So that kind of brings us to the end of the overall analysis of this work. And we conclude with the statement that while the probability of forking under quantum mining is larger than the classical case, it still does not seem to be large enough to be causing problems to the security of the Bitcoin protocol. So yeah, thanks. And any questions?